各位贵宾、各位嘉宾，大家早安，大家好！非常欢迎各位莅临2017年台湾国际科学展览会的开幕典礼暨创意座谈。Distinguished guests, teachers and students, good morning. Welcome to the opening ceremony of 2017 Taiwan International Science Fair. 台湾国际科学展览会缘起于1991年所办理的中华民国参加国际科学展览活动的国内选拔赛，在2002年转型为台湾国际科学展览会。自那个时候开始，就邀请国外的师生来台一同观摩交流，更借这个展览会来评选优秀的作品，选派为我国代表队参加国际科学展览活动。而历年代表我国参加国际科技竞赛活动的学生以及作品呢，不仅让我国的科学教育成果备受国际的瞩目跟肯定，更增强了我国在国际上的能见度，也巩固了我国在科学教育的地位。In 2002, Taiwan International Science Fair was converted from the selecting fair for international activities established in 1991. Since then, it has brought teachers and students and their outstanding science works from around the world for great and profound exchanges in the science event in Taiwan. 2017年台湾国际科学展览会合计一共有国内外师生一共23个国家地区，将近500位的参展师生，有158件的作品进入决赛。本年一共预计在各科选出1等、2等、3等以及4等奖的优胜作品，另外将会从1等、2等、3等奖的作品当中选拔优秀的作品，来代表我国参加美国、荷兰等等国家地区的国际科学展览活动。This year, Taiwan International Science Fair brings together around 500 teachers and students from 23 nations and areas and 158 finalists to compete for awards. 今天典礼的一开始，我们要先来邀请各位欣赏一段表演。我们邀请到国立台湾戏曲学院综艺团，要带来起舞飞扬，降狮献瑞。现在还是元宵节，元宵节都是这个农历年前的新年假期，所以今天特别安排这个表演，希望可以在热烈欢腾的爆竹声以及锣鼓声中，以及旗海当中，为各位来预祝新年快乐，也预祝今年的国际科展成功。To raise the curtain on today's event, now please enjoy the opening show from the troops of acrobatics of the National Taiwan College of Performing Arts. Lucky Lion brings prosperity and good fortune with flag dance. As you know, it is still in the Chinese New Year season, which the performers will bring good luck to every one of us and the great success of 2017's event. So ladies and gentlemen, please all put our hands together for the opening performance. 请让我们热烈的掌声来欢迎今天的开场表演。 现在呢，就要让我们开始来准备欢迎这一次所有参加2017年台湾国际科学展览会的各国学生代表进场了。他们都是各国选拔出来的佼佼者，将在这一次国际科技展览会中呢角逐各项的荣誉。现在我们将依英文字母顺序来介绍各国的学生代表，穿着由他们昨天亲手彩绘的国家代表队的实验袍来进场。Now please put our hands together and get ready for students coming from all 23 nations who are participating and competing for awards in 2017 Taiwan International Science Fair. They will be wearing their national lab coats, gorgeously hand-painted by themselves yesterday, and I'm going to call their name by alphabetical order. So please get ready. So 现在我们大家一起来热烈欢迎这些代表学生进场。我们首先欢迎比利时 ，Now please Belgium. Woo! And show your beautiful lab coat. Wow. And Canada. Wow, cute. And Hong Kong. Very colorful. And Italy. Welcome. And Japan. The Fuji mountain you can see on the left coast. And the next one is Korea. And the last one is Kyrgyz. Nice. And the next one is Macau. And let's welcome Malaysia. And the next one is Mexico. Wow, what did you paint on the back? Very nice. And Nepal. And the next one is New Zealand. And the next one, let's welcome Norway. And the Philippines. And the next one is Russia. And Saudi Arabia. And Singapore. And the next one is South Africa. And let's welcome Switzerland. And Thailand. Nice. And the next one is Tunisia. And then Turkey. And the last one is the host nation, Republic of China, Taiwan. 我们台湾的同学热烈掌声吧！ So this year, the number of the countries hit the highest records ever since. So let's now please get a little bit together in the center and let's have a group photo to mark the memorable moment of today. Are you happy today? Are you expecting the following week? Wow! Nice and welcome to Taiwan. Smile, smile, happy, happy. Have you shown whatever you got in the picture? Okay, thank you very much. Thank you, and please return to your seat. 非常谢谢大家 and welcome to Taiwan. 谢谢，请大家回座。Thank you. 哇，他们的实验袍就是昨天亲手画的，非常的特别，每个国家都展现了他们不同的特色。So every lab coat is really unique and gorgeously hand painted yesterday. 今天我们非常荣幸呢，邀请到10多位嘉宾来到现场，他们都是推动我国科学教育不遗余力，而且长期以行动支持的嘉宾。现在让我来为各位介绍。So let me now introduce you today's distinguished guests. 首先，我们第一位介绍的是教育部林腾蛟次长，感谢次长这边亲自莅临。The Administrative Deputy Minister of Education 林腾蛟 ，Thank you。以及中央研究院廖俊智院长 ，The President of Academia Sinica James C. 廖。台湾国际科学展览会总召集人林荣耀院士 ，Head of Judge Taiwan International Science Fair 林荣耀。教育部国民及学前教育署张永杰专门委员 ，The Senior Executive Officer Division of Junior High, Elementary School and Preschool Education, Ministry of Education 张永杰，以及外交部亚非司张元川专委 ，The Senior Executive Officer of Department of West Asian and African Affairs, Ministry of Foreign Affairs。张元川，张专委，谢谢。以及今天有10多位驻台办事处的贵宾 ，and from distinguished guests from the representative offices in Taipei. Director of Belgian Office Taipei, Mr. Ridwan Gergensbroek. 以及墨西哥商务签证文化及文化办事处的处长。Mexican Trade Services Documentation and Culture Office Head of Officer Mr. Juan Manuel Gonzalez Bustos， 以及纽西兰商工办事处副处长 The New Zealand Commerce and Industry Office in Taipei Deputy Director Duke Solomon Tanoy， 马尼拉经济文化办事处 Manila Economic and Cultural Office Development Cooperation Officer Miss Irene Jungta， 以及莫斯科驻台北办事处的代表 Moscow Taipei Commission Representative Dmitry Polyansky， 以及沙烏地阿拉伯商务办事处 from Saudi Arabian Trade Office, the Ministry of Education, Dr. Abdul Akram。 以及土耳其办事处 Turkish Trade Office in Taipei Deputy Representative Mr. Erhan Gomez， 以及关正孝秘书，非常谢谢。以及我们企业界的代表 from Enterprise Supporter。President of Image Model Corporation 印象有限公司郑金飞董事长，以及英特尔台湾分公司公共事务部刘碧华教育暨创新专案经理 ，The Education and Innovation Program Manager Corporate Affairs Group Intel Miss Rachel Liu， 以及台北市立建国高级中学。徐建国校长 ，Principal of Taipei Municipal 建国 High School 徐建国，以及台北市立立山高级中学柯明树校长 ，The Principal of Taipei Municipal 立山 High School 柯明树，以及最后我们的国立台湾科学教育馆朱南贤馆长 ，The National Taiwan Science Center Director 朱南贤。我们非常感谢各位在百忙当中莅临，也给这个活动支持。Thank you for your participation and great support。现在呢，我们就要来欢迎积极带领国内科学教育发展的教育部的长官来为我们活动致勉励词。Now, Administrative Deputy Minister of Education 林腾蛟 will deliver his welcome remarks. Please put our hands together for welcome. 热烈掌声欢迎教育部林腾蛟处长。
我们中央研究院廖俊志廖院长，还有我们评审委员会董昭廷林荣耀院士，以及我们主办单位国立台湾科学教育馆朱南贤朱馆长，在座的各位贵宾。以及各国代表团的各位团长、各位老师以及参赛的各位同学们，大家早安，大家新年好。
Distinguished guests, teachers and students from all around the world, good morning.
今天非常高兴代表台湾教育部欢迎来自各国的参加我们2017台湾国际科学展览会的各国的这个代表团，各位的选手参与我们第16届的展览会。那么这一次的展览会呢，总共呢有来自包含台湾23个国家，那么有包含了来自22个国家的53位的这个学生代表。跟我们台湾的选手呢，大家一起来这个参赛。那么代表教育部呢，欢迎来自各国的选手，那么一起来参加这样的一个盛会。
Welcome all of you to participate in the opening ceremony of Taiwan International Science Fair. It has been 16 years since Taiwan International Science Fair started, and the number of countries are 23 this year. We received 516 students registered in the beginning stage, and there are 221 students past the first stage judging. In the end, 2017's event brings together 2021 domestic students and 53 overseas students from 23 nations to compete for awards.
其次呢，我也要恭喜我们国内呢。的这个选手那么经过初赛，有将近516位的这个选手，那么来参加这个选拔。那么经过这个评审委员会的这样选拔之后呢，有216位的学生进入到这个复赛。那么每一个选手呢，都是我们国内的各个学校的精英的代表，能够呢跟来自全国国际的22个国家的选手。那么同台呢，那么以科学，那么来进行这个交流，我相信对每一个同学来讲都是一个非常好的一个经验。
As I mentioned that we received 516 students registered in the beginning stage, and there are only 216 students past the first stage judge, and you are all the best.
教育部呢，非常重视我们国内的中小学的这个教育，以推动了全民普及科学教育当做我们的一个目标。所以呢，过去呢，在台湾我们学生在国际的各项的科学的这个学生的能力的一个竞赛，都有非常不错的一个优异的一个成绩。那么就以呢，今年呢刚刚公布的披萨的成绩为例哈，那么台湾呢获得到全世界的在科学竞赛的成绩第3名哈。那么这个成绩非常的优异呢，也显示了我们在科学教育的一个重视。那么为了持续的加强我们学生在科学的这个能力哈，所以在目前研定的2018，也就是107年的课程的这个纲要里面，特别呢针对在自然科学领域的部分，希望能够加强我们学生科学探究与实作的这样子的一个能力。那么希望透过呢科学专题的研究，强化我们学生在科学的探究以及动手实作以及操作实验的这样子的一个能力。那么希望呢学生能够知识跟理论能够相互来这个结合，培养我们学生在科学研究的这个基本的一个能力。
The Ministry of Education devoted to promoting the science education around the country and take lots of efforts to develop science education programs to keep young generation to connect with the international trend. Take an example of the result of the PISA this year. Taiwan ranks the 3rd place in the world. In the new course outline of Taiwan in 2017, we emphasized the scientific exploration and practice more than usual. By doing science research, students could enhance their ability of evaluate and design scientific inquiry. That's the reason we encourage students to participate in the science field.
本次2017台湾国际科学展览会，非常感谢国立台湾科学教育馆的一个主办，那么也安排了非常精彩的这个活动，包含了有教师的工作坊，也包含了学生的交流会。那么也特别呢，待会会邀请我们中央研究院廖俊志廖院长呢，来跟大家做创意的一个座谈，以永续呢作为科学研究的这个新动力哈，那么为题来分享这个大师的一个经验。我相信对于我们所有的与会的学生来讲，都是一个非常好的一个学习。那么廖院长呢，是我们中央研究院的院长，也是我们台湾最高的学术研究机构。我相信由我们廖院长来跟大家做创意的座谈，分享他的这个科学研究的经验。我相信对于我们在座的每一个学生都能够起非常好的一个启发的一个作用。
We highly appreciate the National Taiwan Science Education Center to host this event and put a lot of effort of gathering all different activities in the event, including this morning. We are very honored to have invited President of Academia Sinica, President James Liao, and his the Academia Sinica is the first research institute in Taiwan, and we hope that you will learn a lot from today's lecture and be inspired.
各位选手能够代表各个国家或者各个学校到台湾来参加此次的一个国际科学展览会，都是呢每一个国家跟学校的一个精英。那我们也期待呢，在这一周的展览会，也希望我们所有的选手们都能够彼此来这个交流，那么也能够呢，在现有的这个科学研究的这个基础跟这个兴趣，那么能够呢不断的精进发展自己本身的一个能力。
As you are all selected from your country as the best ones to participate in this event, We expect all of you would be inspired by this event and also enjoy the following week. We believe what you learn during this week will bring the energy and brightness to your future.
台湾呢有非常丰富的人文景观以及美食，我们也欢迎来自各国的选手跟同学们哈，也能够呢有一个非常好的台湾的一个经验，留下深刻的一个印象。以后呢也欢迎大家呢再一次来到台湾。最后呢，祝福我们本次的台湾国际科学展览会顺利圆满，也祝福各位嘉宾身体健康，每位同学都能够收获满满，祝福大家，谢谢各位，谢谢。
And thank you for being here in Taiwan, and hope you will take the advantage to enjoy the beautiful nature and the beautiful food, delicious food in Taiwan, and hope you will enjoy and be back again. Thank you very much and Happy New Year to every one of you. 非常谢谢组长今天的勉励，谢谢。现在呢，就让我们邀请主办单位国立台湾科学教育馆朱南贤馆长来为我们致欢迎词。Now please welcome Director of National Taiwan Science Education Center Zhu Nanxian for his welcome remarks.
Good morning.
Good morning.
Good morning, Administrative Deputy Mr. Lin, President Liao, Academician Lin, embassy representatives, distinguished guests, and all participants. Thanks to Deputy Mr. Lin for your inspiring speech. I also like to record my deepest appreciation for continuous support rendered by Ministry of Education. As the Director General of National Taiwan Science Education Center, I'm honored to welcome all of you to the 2017 TISF opening ceremony. Science is an international endeavor, and no nation can be successful in isolation. International exchanges and cooperation in science is of great significance. We are proud that Taiwan always receives good, even excellent achievements in international mathematics or science Olympiad, International Science and Engineering Fair, ISEF, and the Program for International Student Assessment, PISA, in the past. Based on the above, we are glad to provide a platform for young talent from domestic and from all over the world to exchange ideas and learn from each other. We arrange a series of activities including creative lecture, exhibition visiting, icebreak, event, science educator workshop, science tour, and so on. During this week, please grab the opportunity to build relations and force community that will enrich your perspective. This week of exploration, growth, and networking will stay with you for a lifetime. Last but not least, to all sponsors, teachers, judges, volunteers, thank you for making this fair possible. A journey of 1,000 miles begins with a single step. Let's begin at TISF 2017. Good luck and great success in the coming year. Thank you.
非常谢谢朱馆长 ，Thank you very much, Director General 朱。我们希望透过科教馆的规划跟努力，可以帮助更多对科学有兴趣的学生来长期投入研究的领域。谢谢科教馆长期的努力，谢谢。 接下来我们将进行的就是今天各位非常期待的创意座谈。台湾国际科展每一年为了增添活动的丰富以及拓展国内外学子的视野，从2009年开始呢，就在开幕典礼的期间增添了一项分享，邀请国内科技创意界的大师或是翘楚来分享其研究或是学习过程中值得年轻人参考的经验，比如说研究成果、对环境以及人文的关怀、创意思考等等，也是足以影响人生转弯的宝贵经验。今年我们非常荣幸邀请到中央研究院廖俊志院长。廖院长出生在高雄，在国内完成了基础教育之后，就赴美国攻读博士。他的父母都是工程师，所以受到父母的影响，从小就喜欢研究科学的问题。高中的时候，他对化学和物理都有兴趣，所以选择了包含两者的化工系。1980年代，生物工程革命方兴未艾，又有第二次能源危机，所以让他有了以生物方法制造化学品来替代石化制品，减少环境污染的想法，一脚踏入了生物领域。2012年，他又更进一步以二氧化碳为材料，加上水和电力，以类光合作用的方式产出丁醇，一步到位，同时解决了环保和能源的问题，是少见的美国国家科学院、美国国家工程学院、中研院以及美国发明家学院4冠院士，学术成绩非常卓越。今天廖院长要为我们演讲的主题就是永续作为科技发展的新动力。This morning we are truly honored to have invited President of Academia Sinica, James C. Liao, to share his view on sustainability as a new driver of science and technology. Ladies and gentlemen, Dr. Liao. 我们再一次以热烈掌声来欢迎廖俊志院长。
Well, thank you for the nice introduction. And I'd first like to welcome all of you who come from all over the world. This is truly a remarkable event. This is the 17th event, if I remember correctly. And this is about science. And also, this event is about making friends. Okay, we have so many friends coming from all over the country. So I gave myself a quick test of recognizing what these flags represent. Okay, help me out if I'm wrong. Okay, I challenge all of you to recognize these flags. Of course, we know this is Taiwan. This is Canada. Am I right? Yes. Yes. And I think this is Belgium. Yep. Yes. And Hong Kong, Taiwan again. That's easy. Now, I think this is Italy, right? As Italians, give me applause, right? And this is easy. This is Japan. And this, if I remember correctly, this should be Macau. No?
Kyrgyz Republic.
What?
Kyrgyz Republic.
Kyrgyz Republic.
Yes.
Wow, thank you, Kyrgyz Republic. Okay. And this is Nepal, right? Nepal. Mexico. Am I right? Malaysia. Okay, help me out with this. I thought this was Kyrgyzstan, but that was apparently wrong. What is it? That's Macau. Okay, I got it wrong. This is Macau. And this is South Korea, New Zealand, Norway, Philippines, Taiwan again, Russia, right? Saudi Arabia. Yes. Singapore. Am I right?
Yes.
Singapore, okay. South Africa.
Yes.
Switzerland. Thailand. Yes. Now give me a true test here. Tunisia.
Yes.
Bingo, I'm right. Turkey.
Yes.
I'm doing pretty well. Thank you. Okay, I challenge everyone to recognize each one of these flags and find your friends after my talks. Okay? So, welcome again. This is the International Science Fair. And I was very pleased to be invited to give this talk. As the organizer mentioned, probably not. I was one of the participants 40-some years ago in this type of event. I don't want to tell you how long ago, but 40-some years ago. And I didn't do as much as you guys that came all the way to this event. I think I participated twice. The first one, I think, was I got an honorable mention. The second one, I think I got the third place or something like that. But it was, thank you. Yeah. So I'm sure you do much better than what I did 40 years ago. Okay, so let me start by giving you a few introductions of what I'm going to talk about today. This is sustainability. And why are we talking about sustainability? Can somebody dim the light a little bit? Can somebody 把那个灯光关暗一点好吗？ No, 就是 here. 把台上的灯看有没有办法关掉。No. Okay. Okay. That was an experiment. That's an experiment to see how much we understand our communication. Okay. Science is about pushing limits. Remember that. Science is about pushing limits. Every one of you should push the limit. We try to see very small or very large. So this is what atoms look. What is of course imaginary. Okay, the science, the artist's view of what atoms look like. And this is the This is the electronic orbitals. Of course, this is calculated from quantum mechanics. We try to find out what's happening in the very, very small dimension. And these are the non-living materials. And we also try to see what's within the living organism. So these are cells, this is actually a T cell. And within T cell, this is the structure of DNA. I'm sure by now everybody knows this represents DNA. And each one of you have lots of them in your body. Otherwise, you are not a human being. So we try to see the very small, and also we try to see the very large. So this is the galaxy, the outer space. We see stars, planets, the astronomical events. We also try to cultivate living organisms in large scale. This provides the foods and various plants that we enjoy and sustain our lives. Also, we try to do as fast as we can. So somebody named Einstein, I'm sure everybody heard about him, trying to imagine what would happen if you travel at the speed of light. Okay? And that created the theory of relativity. So science is about pushing to the limit. This is the dimensional limit. Very small, very large, and this is a combination. We try to go very far in a very short time. Now, we have another challenge. We want to push the limit. We want to push the limit to something that is sustainable. That means we want our development, our science to last a long time. That's called sustainable. But lasting a long time itself doesn't mean very much. So there's a definition by Gro Harlem Brundtland. I challenge you. Any of you heard about this person, especially for people from Norway? Raise your hand for Norwegian. This is your prime minister several years ago. Served 3 times as Norwegian prime minister. Okay. She was the first one to define what sustainable development means. That means you need to develop your society that meets the current needs of the society, but does not compromise the need of the future. Okay, so this is a very thoughtful and practical definition of sustainable development. And this has become our new challenge. Why? Because up until now, most of the science and technology that we develop is with the need, with the idea of meeting human demand now. But we seldom think about the future. So let's think back of what has happened. So this is before Industrial Revolution. We use animal as a primary energy source for transportation. And we use biomass as a primary energy, as an energy source. Are they sustainable? Yes, they are sustainable as long as you don't have any demand. But as human society grows, we demand more. We want more convenience. We want to grow. So these become unsustainable, non-sustainable. So human beings trying to harvest oil from whale. Again, this is not sustainable because there are just so many whales that we can harvest. After Industrial Revolution, we began to use mines, coal, natural gas, and petroleum as the primary energy sources. Until now, we are still relying on these three major minerals as our primary energy source: coal, gas, and oil. Are they sustainable? Well, that is a very good question. This is the question that we should all bear in mind. Are they sustainable? Some say that we don't have enough oil. Others say that we have plenty of oil that can sustain our society for another 200 years. But that's the point. It's not just the amount of oil that we need. It's the consequence of how we use these mineral fossil fuels. What are the consequences of these mineral fossil fuels? Let's look at the energy demand. So you are all potential scientists. This is the chart that shows the total energy consumption in the world. In 2015, this is about a year ago, a little bit more than a year ago, the whole world used 18 terawatts. Okay, what is terawatts? 1 tera is 10 to the 12th power. And watts, I'm sure you go back to your house, you take a light bulb. This kind of light bulb, I bet, is about 60 to 100 watts. Okay? Each one of the light bulbs that you see, you raise your hand and look at the ceiling. These are about 60, 80, or 100 watts. The whole world used 18 terawatts, 10 to the 12. 18 times 10 to the 12 watts. We have how many energy that we use. Is that a large or small? Well, most of us don't have any idea since these numbers are so large that you don't care anymore. But let's look at another number. About 15 years ago, year 2000, we were using only 13 terawatts. So in a short 15 years, the energy consumption increased by more than 1/3. So the growth rate is amazing, it's remarkable, it's actually alarming that we increase our energy demand so fast. That created a non-sustainable issue. We cannot continue to use this, increase the energy consumption. So where do we derive our primary energy from these days? From the big three, as I mentioned: coal, natural gas, and oil. These are primary energy sources. The remaining parts are small. Nuclear is about less than 5%. The bioenergy and waste is about 10%. The remaining so-called renewables, hydropower, solar, wind, geothermal, is relatively small. These are the ones that we can count out. These are the ones that are potentially sustainable, and yet we are not using it as much as we should. And that's the challenge of each one of you. Our generation of scientists failed to develop a plausible technology to utilize these renewable energies. And it will be up to the next generations and the generations to come to develop technologies that can change this picture. So what is the problem of utilizing this fossil fuel? At the same time, we are burning coal, gas, and oil. We are seeing a continuous rise in CO2 concentration. When I was at your age, I remember reading the high school book. The CO2 concentration in the atmosphere at that time was about 280 ppm. And look at what we have now, more than 400 ppm, parts per million. Okay. 40 years ago, it was 280. Now it's 405. Is it sustainable? Okay. By the time you reach my age, this number, I don't know what would that be. So this is very alarming. At the same time, when we see the global temperature, the surface temperature has risen more than 1 degree Celsius above 1900 levels, about the turn of the last century. Okay. So we keep seeing that CO2 increases, temperature rises. It's a strong correlation. Why is that? Because CO2 is a greenhouse gas. I'm sure you all know what is a greenhouse. If you close your windows and allow sunshine to come in and your room become very warm, okay, that's a greenhouse effect. And CO2 essentially does that on Earth. So as a result, we see receding glaciers. So this is a picture of the Kai-Trak Glacier in Tibet. This is a picture in 1921, and this is a picture in 2009. You see the glaciers is disappearing. And similar pictures, you can see that on the website, in the internet, everywhere. And this is a famous picture of a bear losing its ground, its ice, so to speak. And this is Patterson Glaciers in Alaska in 1920s, and this is the same site in 2005. You can see that the ice sheets are disappearing. At the same time, we see a lot of disasters, weather-related disasters. In Taiwan alone, we see that extreme typhoons, super mega typhoons, are happening almost yearly that result in various huge damages. And the same thing happened in the United States, in Philippines, Indonesia, everywhere. Okay. So these are weather-related disasters that are linked to global climate change. So we see that fossil fuels are the major sources of CO2 emission. Okay? Gas, oil, and coal. And where do we use this fossil fuel? It turns out that our oil consumption is about 100 million barrels as of last year, okay, 2016. Almost 100, not quite. And we release CO2 about 7 gigatons per year. This is calculated only on the carbon part. Okay, this is 7 gigatons. Okay, here I want you to pay some attention. Okay, I'll give you a quiz after my talk. Okay, now you pay attention. Okay. So the amount of carbon that we release is about 7 gigatons carbon per year. Gigaton is a large number, and you don't have to know exactly how large it is. It's very large. And this is calculated only on the carbon part. The CO2 has a carbon and then 2 oxygen. We only calculate the carbon part. It's about 7 gigatons per carbon. And some other places use gigaton CO2 that's about 2-3 times larger than this number. But we count only carbon. It's 7. Okay? Remember that number. So how do we generate that? So if you drive cars, and in Taiwan and most of the countries, we use kilometers. Okay, so 1 liter of gasoline can drive about 10 kilometers. So you will release about 1/4 of kilograms of CO2 per kilometer. So Taiwan from north to south is about 400 kilometers. So if you drive from the northern part of Taiwan to the southern part of Taiwan, you will release 100 kilograms of CO2. This is how much you dump the garbage into the atmosphere. Driving from north of Taiwan to south part of Taiwan, 100 kilograms. And I bet most of you cannot even lift that much weight. It's heavier than almost all of you. And we are increasing this kind of light-duty vehicles because of population increase, because everybody wants to drive, everybody wants to own a car. So I want you to take public transportation as much as possible. Subways, by the way, Taipei has a very good MRT system, the subway system. If you have not tried that, please try it. It's very nice. So how do we generate these CO2? This is the vehicle. Okay, we first use fossil fuel, go to engine, then burn the fuel to CO2. Efficiency from engine to wheel is about 20%. And this is where we generate lots of CO2. This is for conventional vehicles. Now, what if you use electrical vehicles? Electrical vehicles has a very efficient motor, well, 90% compared to 20% of conventional engine. However, it takes electricity from somewhere. For most places, currently, electricity comes from fossil fuel also. Then you generate CO2 upfront. Okay? Instead of generating CO2 when you are driving. Okay? If you use electric cars, you generate CO2 when you convert fossil fuel to electricity. Unless, of course, you derive electricity from renewable energy sources, solar or wind. So there's a strong need to derive electricity from solar or wind or other renewable energy sources. How about hydrogen? If you burn hydrogen, you are completely independent of CO2. And the efficiency of fuel cell is also very high. But then again, where do you derive hydrogen from? Currently, hydrogen, the most efficient way to derive hydrogen is from natural gas. Here you go. You use fossil fuel again. You derive CO2 again. So no matter what you use, you introduce CO2. Unless you find a way to derive electricity or hydrogen using renewable energy sources, meaning solar, wind, geo, and other renewable approaches. So let's look at the carbon balance in the atmosphere on a global sense. So this is like balancing your checkbook. Okay, some of you may have a checkbook of your own, others you probably look at your parents, how to balance the checkbook. So look at this atmospheric CO2. Now we have 780 gigaton carbon. Remember, we dump 7 gigatons per year into the atmosphere. And imagine this is our balanced book. We currently have 780 gigaton carbon. And we dump 7 gigaton per year. How long will it last to double? And the bad news is that this carbon is not like money in the bank. This is actually debt in the bank. Okay, the more carbon you have, the worse you get. So it's like you borrow a loan from the bank, not your money deposited in the bank. Before Industrial Revolution, this carbon is nicely balanced, either on land or on ocean. On land, there's a photosynthesis by plants that take away CO2 from the atmosphere. And the amount is about 120 gigatons per year. About that 120 gigatons of CO2 fixation, half of them is deposited into soil, litter, and so on and so forth. The other half is given right back to the atmosphere through respiration. We know that plants perform respiration as well. So there's a nice balance of photosynthesis and respiration. On ocean, we also see the same thing. So this is pre-industrial days. Now, after industrialization, we now all of a sudden use a large amount of fossil fuel, including oil, coal, and gas. And like I said, we dump 7 gigatons of carbon into the atmosphere a year. So that gradually perturbs the balance. And the natural processes on land and ocean could not change fast enough to absorb this additional carbon emission from human usage. That is a problem. So what should we do? We should cut down the use of fossil fuel and replace that with renewable sources. For example, we can use renewable electricity. Of course, currently we're using very little amount of renewable electricity, and even if we do very well, we probably cannot replace all the fossil fuels. Okay, let's say we replace half of them, from 7 gigatons to 3.5. That's already very good. So what are the renewable electricities? Number one is solar. I'm sure everybody has seen this. The sun gives us about 120 terawatts radiation on Earth. And we use about 18 terawatts. This is one of my early slides. We use 18 terawatts in as a whole world. Okay, total amount of energy consumption is 18. And yet, we receive 120,000 from the sun. So the small amount of energy we need, if we can capture the solar energy. The wind gives us about 70 terawatts, still much larger than our current primary usage. And the biomass potential is about 6. And so all these, if we derive a little bit from these renewable sources, we could potentially switch our energy dependency on the fossil fuel to those renewables. And this is the picture that many people have seen, the solar panel, and this is actually the solar farm being built in Academia Sinica. And a solar panel is semiconductor materials that can give out charges, separate the electrons and the holes upon receiving radiation. And this type of devices has been invented many, many years ago, but efficiency and cost are issues. Okay? And it turns out that the efficiency limit. As you work on science, okay, you will know that everything has a theoretical value and practical value. And solar panel has a theoretical limit of how efficient it could be. And it turns out that the most efficient solar cell cannot exceed a limit of about 33%. Okay, this is the efficiency limit of solar cell for a single junction solar cell. Of course, you can use 2 and 3 and 4 of those, and then you link them together, the efficiency can increase. But if you have only single junction, the limit is 33%. This is the famous so-called Shapley-Quasar limit. And currently, we are doing about 15 to 20%. So we're doing pretty well. And the problem is that it is expensive. Okay, the current solar panel, although cheap enough, but still more expensive than fossil fuels. So that is why when we develop new technologies to replace existing ones, we have to consider both the science, the efficiency, and the economy. Okay. If the technology is too expensive, it will not be commercialized, will not be implemented. So for the future, one would like to build technologies that allow one to use flexible panels for solar cells, okay, that has high efficiency, and we should not use rare metals. We should use earth-abundant materials. And inexpensive and low contamination. We don't want to develop a process that causes a lot of garbages that we cannot treat. And so that is a sustainability consideration. And also, we need to develop technology that allow easy installation and removal. And a few of these kind of technologies have been proposed. One of them is the organic photovoltaic cells. Okay, it turns out that photovoltaic cells you can make of organic materials instead of using silicons. Although the efficiency currently is still very low, it's about 8% compared to 15, 10, 20% of the silicon-based solar cells. But it is cheap, and it is the energy payback time called the ET is very short. Right? So it's a low-cost, low-energy manufacturing. And CO2 emission factor also very low. So this is a potential direction, even though it's still some time away before its commercialization. Another interesting and promising approach is something called the perovskite solar cells. The perovskite is a special structure, okay, shown here. Okay, the metals in red and in dark color here. The red and this black are the metal. In this particular case, the metal is the lead. This gray or dark ball represents an organic and inorganic combination of materials. Usually this is the metal aluminum ion. Okay. The green ones are the halides, the negative charged materials. So this is an interesting structure that has been found in many, many places. And this structure is particularly interesting because you can use many different materials to make this kind of structure. And this structure allows you to tune the band gap of a material. So you can tune the efficiency and where the material can absorb, can emit energy, and so on and so forth. So it has the potential to build very high efficiency solar cells. And since 1985, as you can see, the improvement is very rapid, especially in recent years, is approaching the conventional solar cells. And it's expected to exceed the performance of current solar cells. So it has a high efficiency and tunable band gap, as I mentioned. There's easy fabrication because this allows what we call about using the flexible materials to make solar cells. So it's much more efficient in manufacturing. It has some problems, at least currently. It uses toxic materials. There's a lead in here, and that's a get rid of lead. Otherwise, it's problematic. And it is environmentally unstable. Okay, this material is fine, but it's not very stable. Okay, it cannot last very long. Okay, so these are all the problems that deserve your attention. Okay, by the time you reach your college or graduate school, you may be working on this type of problems or even beyond. Another way to harvest solar cells is to convert solar energy to heat. Okay, the solar thermal unit. Here, the concentrator to concentrate the solar energy to a point that heat up the material, maybe water, maybe salt, maybe other mediums, and then use that to generate electricity. Okay, this is also being tested, and a few companies are commercializing this type of technology. So that was solar. Wind also is a very possible renewable energy. And human beings have been using wind power for many, many years. And I'm sure you've seen this type of pictures. These are Dutch windmills. And it's very low tech, and efficiency is not very high, all the way to current day wind turbines. Okay, the efficiency has come from about 15% to more than 40%. And because of these advances that allow us to harvest wind energy much more efficiently and become commercially plausible. And here's some complex science and math and physics involved. So imagine this is a wind turbine, and this is the incoming wind, this is downstream of wind. So you can perform some physics calculation and some math modeling to convert the energy from wind to the mechanical energy represented by this windmill. And you can calculate a theoretical value, just like I mentioned. In solar cells, there is a theoretical limit of efficiency. In windmill, there's also a theoretical limit, and that is 50%, 59.3%. Okay, this is called the best limit. So this is why you need to learn science. Okay, you know what you can do and what's your limit. And being a scientist, you not only need to be brave, but you also need to know your limit. And you cannot defy scientific laws. Okay? And it turns out that the efficiency, and the power that you can harvest from wind turbine is proportional to the speed ratio and the area that you cover. Okay, as you can see, and this is a 4 megawatt wind turbine. Has a diameter of 120 meters, a huge wind turbine that can produce 4 megawatts of electricity. How much is 4 megawatts of electricity? That can power 800 to 1,000 houses. And it's American houses, so American houses use a lot of electricity. Okay. So 4 megawatts using this type of turbine can power almost 1,000 households. And currently people are building this even larger 7 megawatts windmill at 140 meters. So this is coming very soon. And like I say, each one of them can have 7 megawatts, from 4 to 7 megawatts. A power plant, a nuclear power plant, is about 2 gigawatts. So we only need to have about 1,000 of them to replace a nuclear power plant. And there are various places have installed this wind farm. Denmark and the Scandinavian countries, I'm sure Norway has some in that region. Netherlands, those are the good wind farms. And not only in the Scandinavian countries, in Taiwan also has a very good condition for harvesting wind power. The Taiwan Strait is one of the best wind farms in the world, okay, because wind comes from this area and squeeze between mountains. And so as you can see that about 50 in top 100 best sites are in Taiwan Strait, shown 50% by China and Taiwan. So there's half of the sites, so one side each. So in Taiwan Strait, there's a large number of sites that can be used to harvest wind energy. However, this is not easy, as you can imagine, that harvesting wind energy from the ocean involves a lot of technological challenges. And what happens if typhoon comes, extreme weather comes? You need to build a very strong structure to withstand that. And that requires a lot of investigations that rely on people like you, the young scientists and young engineers, to work on this type of problems. So one problem of these renewable energy, solar or wind, is that it does not happen all the time. It's intermittent. Okay, we know that wind blows and stops. It comes and goes. And sunlight, of course, disappears at night. When clouds move in, your sunlight dims. So these are intermittent energy. And when sun shines or wind blows the hardest, you may not need to use the energy at that time. So you need to find a way to store the energy. And that turns out to be one of the most difficult problems of renewables, is the energy storage. Energy conversion is relatively easy, at least we have solutions. Energy storage is a very difficult problem, and so far the solutions are not very good. And this picture shows various type of solutions that we can see. And most commonly, the way you store energy is using batteries. And everyone has one in your hand, in your pocket, cell phone. And cell phone has a battery. I'm sure everybody has that. And I'm sure when you want to make the most important phone calls, you find that your battery is out of power. And a few months later, your battery breaks. Everybody has this experience. And your phone works, but your battery goes bad, and you have to throw away your phones. These are common problems for almost every single person. And people as young as you guys, you already experienced this, I'm sure. Batteries has a lot to demand. Batteries has a lot to improve. And not only that, if we use battery, this is a lithium-based battery, lithium-ion battery, the capital requirement and technology risk is one of the highest. And the easiest way to store energy is using hydropower, and a very straightforward way of pumping water uphill. When you need it, you use water hydropower to generate electricity. So use an artificial way to build a dam to pump water up and down. And this is as advanced as we can get. And there are many other technologies in between, but the lifetime is long, it is short. Okay? The lithium-ion batteries, the efficiency is high, but it work into the energy storage area. How about hydrogen? We can use renewable energy, electricity, to produce hydrogen. And I'm sure many of you have done this type of experiment. Take a battery, okay, and put a copper wire on both positive side and negative side, and put that in water. And what do you have? You have electrolysis. You generate hydrogen. You can generate hydrogen, but the problem is that you have to store hydrogen, and this becomes another problem. Hydrogen storage is a problem. And then when you utilize hydrogen, you go to the fuel cell, and that is also a problem. And fuel cell has been developed almost 100 years ago, but the efficiency is not very high. So, and then fuel cell generate energy. So you can think of this as a hydrogen battery. So to replace a simple battery, you generate hydrogen, store it, and convert to electricity again. So it is still involves many different challenges. So hydrogen is great, but it has a lot of challenges to overcome. How about bio? Okay, many of you are interested in biology. It's one of the most exciting areas. So how do we contribute to this renewable energy using biology? Why do we use biology first? It has very precise chemistry. Okay, some of you may have learned, some of you may have not learned. Biology compared to chemistry is that it has a very precise chemistry, unlike the non-biological reactions. The biological reactions can precisely conduct exactly what it's supposed to do. And it has the ability to make different types of fuels. It's environmentally friendly because it doesn't operate at high temperature or high pressure. It doesn't use any toxic materials, at least much less. And potentially inexpensive. I say potentially because we are not there yet. Okay, it could be inexpensive. And also it can make the liquid fuel that is much more dense than the current battery. So this is the gasoline that we use today. It has an energy density of about 50 times higher than the lithium-ion battery. So a small amount of liquid fuel contains the energy that is contained by this large number of lithium-ion batteries. So when you drive electric cars, you are practically driving on a set of batteries. Okay? And yet, if you use liquid fuel, it's only a small amount of liquid fuel. So this is pros and cons. Liquid fuel is not as clean as battery, but the energy density is very high. And so the challenge is either to reduce the volume or improve the energy density of battery, or to making this liquid fuel more renewable. And some of you may know, others may not know, that currently we derive energy using this kind of refinery, the petroleum refineries. And like I said, biology can conduct a lot of different kind of chemistry. So we can potentially shrink all these into a bacteria cells. We can engineer bacteria cells to produce many different kinds of chemicals. So instead of using a complex petrochemical plant, we can now use a bioreaction, a single cell or plants for that matter, right, to produce chemicals that we are interested in. So why do we want to do that? Because this is obviously much more environmentally friendly. But it's not easy. It requires a lot more of research and development. Okay, this is too slow currently, and quantity is not enough. And this is inexpensive, but it's environmentally problematic. So why are we particularly interested in biology? Because it has one very unique feature, that it can fix carbon dioxide using sunlight. I'm sure every one of you learned this in high school, either in junior high or in high school right now. Plants and many microorganisms can harvest sunlight, converting light energy to chemical energy that can be used to drive CO2 fixation through something called the Calvin cycle. And we can fix CO2 to sugar. And this sugar makes the plant biomass. And then we can break down the plant biomass to fuels and chemicals and to whatever. Okay, so this is the scheme that most scientists are hoping that we can achieve someday to replace petroleum. So the current scheme is the following. We use plants to fix CO2. Of course, plants make a lot of plant biomass and food as well. So for example, this is a corn. I don't know if this is corn or not, but suppose corn. We take the corn, the edible part, we eat it as food. The remaining part, the corn stover, and the remaining part don't eat. We can convert that to sugar. Okay, those are the parts that we cannot eat. And then this sugar, we can convert that to fuels such as ethanol. And we can drive ethanol, using ethanol as fuel to drive our cars. And release CO2 again. So this is a full cycle. So the CO2 we release will be recycled back to fuel. Alternatively, we can use microalgae, cyanobacteria, or various kind of photosynthetic microorganisms. And instead of making sugar, we can make this kind of lipid long chain fatty acid. And these are diesels. So there are many different kinds of chemicals that we can make, okay, depending on how much you want to manipulate. And this is a complex slide summarizing everything we can do in biology. We can harvest sunlight, converting light to ATP, which is the energy equivalent that cells can use. Okay, we convert solar energy to bioenergy in the form of ATP and electrons, and use that to drive Calvin cycle to fix CO2. And we make sugar from CO2. Some of the sugar is stored in cellulose that makes cell walls. CO2 is then broken down to various compounds, make alcohols, fatty acids, lipids, and so on and so forth. Now, why is this interesting to us? Because each one of the reactions is catalyzed by a protein. And protein is made through the DNA codes. And we now have the ability to edit DNA codes precisely what we want. Just like we take a piece of paper and a pair of scissors. We can cut, we can paste, do anything we want, at least in theory. So now we can take a piece of DNA, we can change this piece of DNA using the current day biotechnology. By changing DNA sequences, we can change protein properties, and therefore we can change the kind of chemistry that we perform. Instead of going to this way, we can make that to make alcohol. Instead of making this type of alcohol, we can make the cell to make other types of alcohols. And these are all possible now. So in short, we can now rechange everything inside the cell by doing genetic manipulations in a very precise manner. And therefore, many people have demonstrated that we can engineer microorganisms to make a large number of different compounds, and here we only show a few. Okay, we can make a lot more than these that we show. And we can do that not from sugar, we can do that directly from carbon dioxide. Okay, remember, there are many organisms like microalgae, and this is cyanobacteria. Cyanobacteria is one of the oldest organisms that evolved on Earth. Okay, it's responsible for the oxygen that is present today on Earth. When cyanobacteria was evolved many, many millions of years ago, the Earth began to evolve oxygen. Because of photosynthesis, it splits water to make oxygen, and therefore we have oxygen to breathe today. So this type of organisms can harvest sunlight to fix carbon, and what we can do is take some of this DNA, we rearrange that, we design the way we want it to make the specific chemicals that we are interested in. For example, if you are interested in ethanol, isobutanol, or various kind of fuels that you are interested in, or chemicals, you can do that. And therefore, you can demand this type of organisms to convert carbon dioxide to the kind of chemicals that you are interested in. So this is an example that my student has done in my laboratory a few years ago. This is cyanobacteria, looks green, and absorb light, and you can evolve a compound called isobutanol, isobutyraldehyde, directly in the head space. So giving sunlight, it converts CO2 to this kind of fuel. Now, photosynthesis is great, but can we make it better? Okay. We know that photosynthesis is taking sunlight, we separate the charge. This charge separation is one of the energy harvesting events. And then we use this energy to fix carbon dioxide to make biomass, and then eventually make biofuels. However, like I said, everything has a limit. We already see the limit of solar cells. We also saw the limit of wind turbine. Now here's the limit of photosynthesis, the efficiency limit of photosynthesis. People have calculated that from sunlight to biomass, the most efficient plants is about 4.6 or 6%, depending on the types of plants. And there are two types of plants grossly. One is called C3 plants, the other type is called C4 plants. For those of you who have not learned this, C4 plants are more efficient in photosynthesis. Okay. And what are C4 plants? Okay. Maize, which is corn, sugarcane, sorghum, those are fast-growing, fast CO2 fixing plants. And most other non-crops are C3, are less efficient. In practical situations, this photosynthesis and CO2 fixation together is efficiency less than 1%. And how does that compare to man-made devices? As I mentioned, the photovoltaic cells can turn electricity, turn solar energy to electricity with an efficiency of about 10 to 20%. And it's a theoretical limit of 33 or 34%. It's called the Shapley-Queisser limit we mentioned earlier. So here's a man-made device that can achieve 10 to 20% practical efficiency. And this is the natural photosynthetic efficiency. It's less than 1%. How do we combine the two to make photosynthesis more efficient? So here's the challenge. Again, go back to your high school biology book. Photosynthesis can be divided into two parts, roughly. One is called the light reactions that harvest sunlight to make ATP or electron donors like NADPH. You don't have to know the details. It harvests sunlight, converts to something that the cell can use to drive the dark reactions, the so-called dark reactions, which is carbon cycle. This is what plants or microorganisms do. But if you can separate these two, you can separate the light reactions from dark reactions. And we utilize the man-made device to perform the light reactions because we are so good in converting solar cells into electricity with a very high efficiency. Now, if we can utilize this electricity to make the compound that the cell can use to drive Kelvin cycles, then we can link the man-made device with biological devices and achieve higher efficiency. And this is what we proposed to do a few years ago. We use solar panels to generate either hydrogen or formic acid. And formic acid is also an intermediate that can be used to power Kelvin cycle. And then we can engineer the microorganism to produce fuel by using genetic engineering. If we can accomplish this, our efficiency is about 9% theoretically, compared to less than 6% using this type of all biological reactions. So after a long try, we have accomplished this direct conversion of CO2 with the help of electricity. Now, we don't need sunlight to make photosynthesis anymore. We can use electricity to drive photosynthesis. And this electricity can come from the grid, or you can directly using solar panel to harvest sunlight, convert sunlight to electricity, and then use this electricity to fix carbon dioxide to make fuel for you. Although this is an early day demonstration, but this demonstrates the possibility that this can be done. You can combine both the man-made device with naturally evolved microorganisms with genetic engineering techniques. You can do a lot. Of course, I want to caution you that this is not practically possible yet, okay, not commercial scale, so it still requires lots of research and development that depend on you guys, young scientists and engineers. So what we have accomplished is instead of using sunlight to fix CO2 to make fuels, we now cut the sunlight, this part, we take electricity from sun, okay, the solar electricity, and use that to power microorganisms to make fuel. Another problem which I think I should skip with the time limitation. I'm not going to talk about this problem. And instead, I'm going to talk a little bit about this. CO2 fixation, although it is probably as much as efficient as we can get today, but it still has a lot of problems. For example, we use this protein called Rubisco. And this is something that you should also remember. Rubisco is the most abundant protein on Earth. If there's one protein that is the most abundant, that is Rubisco. All plants, everything that fixes CO2 requires, not everything, but most organisms, plants, almost all protected plants, requires Rubisco to fix carbon dioxide. And Rubisco is a very complex protein. And even though it's evolved by many millions of years, almost to perfection, but the efficiency is still very low. Why? Because it cannot distinguish between carbon dioxide and oxygen. It is supposed to fix carbon dioxide and produce 2 molecules of 3 carbons. This is what it's supposed to do. But in the presence of oxygen, this Rubisco cannot distinguish the 2 molecules, oxygen and CO2. To Rubisco, they look the same. They look very similar. So it can perform this alternative reaction called photorespiration, and that decreases the efficiency of photosynthesis. So people have tried to improve this Rubisco for many years, but without any success. So this is yet another challenge for young scientists. If we can develop another way to fix CO2 without using Rubisco, another way to fix CO2, we can improve photosynthesis dramatically. Another problem that we are facing today in all over the world, in addition to CO2, is methane. And many of you know that methane is also a greenhouse gas. In terms of amount, methane is about 10% of, contribute to about 10% of greenhouse gas. It's a smaller number compared to CO2. However, the potency of methane is about 30 times worse than CO2. So 1 molecule of methane is as bad as 30 molecules of CO2. So methane, even though we don't produce very much, but it's a very potent greenhouse gas, meaning it's very bad. And yet, we produce a lot of methane unexpectedly. How do we produce methane? Animal farming. Cows produce a lot of methane. If you have go to a farm, a cow farming farm, you smell it. And chicken farms and pig farms also produce a lot of manures. Those manures put together, a few weeks later, they smell really bad and produce lots of methane. And currently most of this methane is emitted to the atmosphere, causing a lot of problems. So it would be great if we can utilize this methane, and the easiest way to use that methane is to burn it. Okay, this is an old technology, we can burn it, use that in the kitchen to cook food, or to generate electricity. So these are all possible. But those are not economical yet. What if we can convert methane to something that we can use in a more efficient way, that is convert methane to chemicals? And this turned out to be a very difficult problem and requires a lot of attention, and probably will not be solved until young scientists like you guys become mature scientists. This is a molecule of methane, and you can see it doesn't have any features. It's a carbon and 4 hydrogen, and very symmetrical, very slippery. And it's a very difficult process to convert methane to methanol, and this begins to have some functional group that allow people to derivatize to make various chemicals. And this process is very difficult. And currently, one can develop some enzymes that a few groups in Academia Sinica and other places in the world are working on this. Or you can use biological ways. There are enzymes such as PMMO, SMMO. Those are naturally evolved enzymes that can convert methane to methanol. And using a microorganism called methanotropes that natively evolved, we can do this. So there are a lot of different ways that you can go about. And that's why you need to learn various types of sciences: chemistry, biology, physics, and math. And in addition to these energy problems, we see drought, we see extreme heat that cause problems in agriculture. So it is important for us to develop technologies that can produce drought-tolerant crops, such as drought-tolerant rice, as I shown here. Or on the converse, we see flooding almost on a yearly basis. The submerged-tolerant rice is also important, and other crops. Finally, all these problems don't just affect the environment, they affect our human beings personally. Air pollution comes from these fossil fuels. So everybody is experiencing that. It causes asthma, cardiovascular diseases. This extreme weather causes changes in ecology that promote the development of malaria, the dengue heat, okay? Dengue fever that we see every year in Taiwan and in many countries, and so on and so forth. So all these problems are not just environmentally oriented only. It affects intimately each one of us in terms of our personal health. So it's an important problem to all of us. So I hope that through this short presentation, at least you get a sense that science and technology need to think about future sustainability. And there are a lot of new discoveries and developments that are needed to solve the current day problems, such as CO2 accumulation. And we have a lot of challenges. It's not an easy problem, but at the same time, they also represent opportunities for each one of you. So it's a difficult time, but at the same time, it's also the best time for you to work on these problems when you are young. Thank you very much, and I'll be happy to entertain any questions. Thank you.
Thank you very much, President Liao, for sharing this much and valuable information and insights about the threats, challenges, yet opportunities of the globe sustainability. I think while you were talking, many inspirations and also maybe many new ideas might have been coming out. But before we open the floor for questions, I would please allow me to introduce some more of the distinguished guests this morning. 现在我再补充介绍几位今天早上出席的贵宾。From the Italian Economic, Trade and Cultural Promotion Office, Representative Donato Sciascioli. Thank you for coming. And from the Saudi Arabian Trade Office, the representative, His Excellency Talat Ibrahim Al-Muslemani. And also the Chief of Visa Section, Mr. Mohammed Ehsan Kashan. Thank you very much for being here. So now we open the floor, and please take the good opportunity to raise some questions to President Liao. 现在我们开放现场提问，大家一定要好好把握这个时间，来，请尽情发问。我们接下来大概还有20-30分钟的时间。如果要提问，请举手。哎，这边来，这边我们请现场工作人员给麦克风。麦克风在哪边？好，来，工作人员请赶快是跑步。谢谢。
I'm curious, what component of our what component of the solar speaker solar cell? Okay, thank you.
Perovskite the solar cell. The structure is what I shown earlier. It depends on how you make it. There are many possible components. Let me show you here again. Here. So usually it's a lead. Okay. This atom is lead, and this is metal ammonium. Okay. And this is usually halide ion, iodines, chloride, and so on and so forth. So many people are trying to alter these compositions, trying to find the best performance material. And as long as you have this structure, it's called the perovskite structure. And it can perform many interesting properties. And so the composition still can be optimized. Did I answer your question? Okay, thank you. Anyone else? Yes.
Thank you, Professor, for...
Please announce your the nationality.
I'm from Nepal.
Okay, good,
yeah.
thank you.
And thank you very much for your informative talk, and it was very inspiring. So I'm also working on this solar cell, so I have 2-3 queries, or you can say curiosity. So you didn't put nuclear, means nuclear power in sustainable, where nuclear is not only about the fission, also about the fusion. So fusion is one of the means like sustainable energy, and it's already in construction. You heard about tokamak, so it can be the one of the best green energy. Second is you wrote about some third generation solar cells, that is DSS, means DSSC, dye-synthesized solar cell, and quantum dots. So we are also making that, and in Academica Sinica, hopefully you are making. So we are also facing problem of stability of efficiency, because we can make the efficiency up to 6 to 11, but when we take it out of the lab in the sunlight, it decreases less than 1. So what research are you doing there to stabilize the efficiency of the solar cell and the durability duration of the solar cells? Thank you very much.
You raised a very important and interesting question. So first about nuclear fission, and it's still science and technology that has been developed. I know the two places are working on that. I didn't put on here because still could be pretty far away. You're right. It's if it works, it's the best in the world. But the chances are still out there. We don't know how feasible it is. Then the second question is about stability of solar panel. That is again a problem. Okay, you can do very well in the lab, okay, but it's not sustainable. Okay, so being in the lab, being successful in the lab doesn't mean that it's successful outside the world. Okay. So that is part of the challenges of sustainability. That you need to do that under the most realistic environment or even most challenging environment that you could face.
Thank you very much. And one more,
Okay.
yeah, please. So why don't means like we or you, anyone, are thinking about the solar pockets, that we can just capture the solar photons in a material, and we install it in a solar cell, like you have mentioned that dye-synthesized solar cell, there are layer by layer, and we can put somewhere the material, and it will randomly send the photons, and the reaction continues even there is darkness.
Well, if you can invent that, that would be great. But it has not been invented. Yeah. Anyone else? Yes.
Hi, so I'm from Canada, and I was wondering, do you think it's better to have a system that creates electricity from clean systems, or to create clean hydrocarbon fuel? So like taking CO2 from the air and creating oil instead. So which one do you think is better?
Okay, very interesting question, and this is also a strategic debate among scientists. Okay? No one has a clear crystal ball to find out which direction will win first. So common strategy is to pursue all possible routes. We don't know which one will be successful first. And of course, if you can develop everything without carbon, that's a possibility. Okay, but if you cannot, recycling carbon is important. And more people feel that even today, if we stop emitting CO2, we will not solve our CO2 accumulation problems. Okay, we'll still need to find a way to capture CO2 from the atmosphere. Okay. And like I said, it's a strategic problem. Okay. My sense is that it will be very challenging if we want to completely do away from carbon-based materials and fuels. Okay. Not theoretically impossible, but it's very, very challenging. So the most common strategy is to all of the above. Okay. To develop carbon-free materials, carbon-free fuels. At the same time, making the carbon-based processes much more efficient, or even to capture CO2 from the atmosphere. So that creates a lot of opportunities for everyone. Yes?
My name is Kozaki, come from Japan. I want to ask two questions.
Mm-hmm.
Why the time? Taiwan, what this time means speed of development technology. Photosynthesis or artificial photosynthesis is a future technology. Almost, I heard 20 or 30 years back, but still on the way to develop. if you see the development of economy or population, it's much faster. We have enough time to develop our technology or not. Another point is the volume. If you see the technology, it's successful. But if you want to demand people demand, if you want to provide a huge amount of energy, it's still sustainable or not. If you think about oil, if you want to use a little amount of oil, it's sustainable. But we need a large amount of oil, so it's not sustainable anymore. At such point of view, if you want to use the solar energy or wind, we want to provide a huge amount of energy. It's still sustainable or not.
So you also raised a very interesting question. The short answer is that we as a human society don't have any good solutions. No one can point the direction that this is sustainable, this is the solution. No one has that. Every solution has a problem. Every approach that people propose is still under development. And you are absolutely right. A scheme that looks good on paper doesn't necessarily mean that it's plausible in a large scale. There are lots of different considerations that you have to put into it. And that's the take-home message of the talk today. And there are so many different aspects. And being successful in the lab is only in the very, very beginning. Does not mean that it will be development. However, on the other hand, the reason why I'm here is to encourage young people not to be discouraged by those daunting tasks. If you think of things are impossible, nothing will move forward. If you think that this is not possible, that is stupid, then nothing will move forward. For young people like you, I think I want to encourage you to be brave, to propose new ideas, even if they are wrong, even if they are eventually not practical. But you are young, and you have the license to make mistakes, in science at least. Propose new ideas, propose new approaches, to experiment new directions. Most of them will fail. Majority of them will not be practical. It will not necessarily solve everything that we have faced today. You're absolutely right. But if you don't try, you have zero opportunity. Anyone else? We have a lot of questions from international friends, and that put a pressure on our domestic audience.
Hi, I'm from Mexico. I'm a student from biotechnology economics. So my question is, how do you see this biotechnology application in the future, I don't know, in 20 years, in the problems with the petroleum material?
Which one? The
For
biotechnology?
example, the application from the biomolecule applicants for the plastics.
Or biomolecules, you mean?
Yes.
Okay, depending on how you call it a success, okay? And biofuel has been in practice in Brazil for many, many years. So in Brazil, it's a success, okay? But that has a unique environmental and economical structure to its success. In the United States, bioethanol has also been implemented, same as in many different other countries. Also, there are quite a few commercial factories that have been built that are using the lignin cellulosic materials, not the food part, okay, the unedible parts, and try to convert that to ethanol. So quite a few plants are being built as we speak, and whether they will make economical success is still remains to be seen. But it's many people hope that this kind of development is on the right direction, and that's what we should push for. Yes.
So maybe I'll ask you directly. Thank you for your inspiring speech, and it seems that your speech is focusing on to realize sustainable future on the technical aspect. But how about we can use a more practical way on the economical aspect, like carbon tax? What's your opinion about this? Thank you.
I'm not a tax expert, but intuitively I think it makes sense. I think it makes sense that what we use all these days, whatever that we pollute, we pay for it. Okay? And I'm sure in most developed countries or in many cities, you pay for garbage removal, right? You have to pay for people to remove your garbage. And yet, we don't treat carbon dioxide as a garbage. As I mentioned, if you drive from northern part of Taiwan to southern part of Taiwan, you'll produce 100 kilograms of carbon dioxide. And you just conveniently roll down the window, throw it out, okay? As if nobody cares, nobody watches. Okay? I don't have to pay. Okay? So intuitively, I think that it makes sense. The problem is that how to implement that in the fair way and gradual way so that it doesn't completely collapse the economy. And that's a huge challenge.
Hello,
Yes.
Excuse me. I'm Aziz from Saudi Arabia, and I have a question. Many energy storage methods may cause environmental pollution. So, is there any technique to store energy without pollution or be environmentally friendly, and how does it work?
You asked the ultimate question, is there any technology? No, nothing is available right now. Nothing is perfect. Okay? So everybody trying to go many directions and trying to find a workable solution under a particular environment. Okay? So one scenario is that maybe there are many solutions and each one works under the particular environment suitable for that particular country or that particular city. Okay? So unfortunately, there's probably no perfect solution like that.
Okay, thank you.
This is another question from Saudi Arabia. My name is Abdullah. What I'm thinking of as a scientist, as a scientist, why we should keep and generate a solution for the problem while the government still use all of this CO2 productions, all of this works just for making our earth worse and worse. My question is, when that days will come and we will just stop all of this thinking of our earth or our planet, we just keep and generate a solution without any real applying for the real life. That's my question.
It's also a very good question, and so that's social cultural aspect, maybe even political aspect. Okay, why are we still doing it, knowing that it's so bad to burn fossil fuel? Why are we still doing it? Well, unfortunately, we have a lot of basic needs. Suppose that we completely shut down the fossil fuel, okay, and rely on only the renewable energy, and guess how much energy that we can get. And it's very small amount of energy that we are using, we can derive today. It's only this amount. It's not practical. Unless all of a sudden we say that we don't watch TV. We don't use cell phones. I don't buy cell phones. I don't read. I use sunlight. And our human society has advanced far enough that we are completely dependent on the current day energy structure. So it's not a matter of yes and no. It's how we can gradually transition to the better world. Yes.
I'm Joshua from the Philippines. My question is, what's your opinion on the development of artificial photosynthesis as a solution?
I'm currently working on that myself, so I'm optimistic, but somebody said that it's still very challenging, as many people have attempted the similar ideas or various kind of ideas for many decades. It's still a long way to go. That should not stop any of us. Okay? Being scientists, one of the prerequisites of being scientists is being brave and optimistic. You cannot always be pessimistic. Okay? You have to have a sense of optimism and believe in yourself, believe in your intelligence, that someday you are going to solve part of the problem, even if it's not completely. You solve part of the problem, and everyone works together, solving part of the problem together. Maybe someday we'll solve the whole thing together. Yes, somebody back.
Hi, I'm David from Taiwan. And okay, so but I know there's renewable energy like solar and wind. Everything is growing right now. But recently, for recent years, fossil fuels usage and its percentage is actually increasing because of the decline of nuclear. That everybody we think is internal pollution and nuclear waste. So, but on the other hand, nuclear energy right now is considered cost is the most recent solution. So, do you believe that nuclear energy is a transition phase between fossil and renewable energy for applying for substitution before renewable energy actually grow to commercial usage? Thank you.
Nuclear energy is a complex issue, not just a technological issue, but also social, economical issue. Where do you place your resources and how much risk you want to bet? In short, if nuclear energy doesn't generate any nuclear radioactive waste, it's a reasonable solution. But I'm sure you don't want to have nuclear waste sit in your backyard. Okay? If you don't want the nuclear waste in your backyard, why should you demand other people to take your waste? Same idea that we have seen before. Okay? So that is a social cultural issue with a lot of political implications. The whole world is still yet to grapple with. A lot of debates all over the world as to whether we should or should not use the nuclear in the meantime to buy some time. But don't forget, building a nuclear power plant is not cheap, it's not easy, and it's not completely energy free. So lots and lots of issues. This is a problem that cannot be solved on paper. And that is exactly why I want to encourage young students to think of new and novel approaches. And somewhere back in my mind, I believe that we have not seen the real solutions yet. Every solution that we propose to do, ranging from solar to nuclear, from bio to CO2 fixation, artificial photosynthesis, none of the things that we talk about could be real. The real solution may be still yet be in one of you guys' mind. We don't know where that is. And I think that is the driving force for us to move forward. That is the driving force for science and technology. Okay?
Thank you.
There's one back there.
So as we know, the society is.
Which country are you from?
I'm Jonathan from Taiwan.
Okay.
And as we know, the society is often blocked from the newest technology, and scientists often cannot really realize the needs of the society. So as a scientist, so what do you think the scientists should do to solve this problem?
Scientists should work harder, that's all. Be smarter and work harder. I think everything we said, the practicality is not there. It's not because no one wants to use the whatever scientists develop, it's that we're not good enough. Okay? Everything that we have talked about, we have proposed, cannot solve completely all the problems. We all know that. But that does not stop us from doing it. We keep trying. At the same time, we should not demand the society to accept what we say as such. And we cannot be that arrogant, we not to be that ignorant to think that whatever we propose is going to solve the whole world's problem and the rest of people are foolish not to listen to us. No, that's not the right attitude either. Okay? Everything we propose is right for one angle, but wrong for many others. And we need to listen and consider all other aspects. And we cannot solve all the problems simultaneously. So it's okay that we focus on only one aspect to solve it, to perfect it. And don't be discouraged if other people tell you that this is not practical because of this and that. Okay, you listen to that, you think of other solutions along the way. Be mindful of those limitations. Okay? But don't be discouraged. Okay? Everything you develop cannot be immediately solve the whole world's problems. Not yet. Okay? And until you try hundreds of times, and nothing is going to be practical. I'm sure growing up in any place, you heard about many failures of famous scientists and inventors and engineers. Right? And that's the spirit. That's a true thing is happening. It's not just in a textbook. Okay? So we need to keep trying, keep inventing, keep improving our technology and discoveries.
Thank you.
Hi, I'm Victor. I'm also from Taiwan. Well, thank you for your speech. I've heard that you are doing artificial photosynthesis. Is that right? So, what I perceive, because my English isn't very well, so maybe I've missed some things, but you use solar power to create electricity, and this electricity would complete the remaining reactions. So, I don't want to be offensive, but what is the purpose of artificial photosynthesis if it still needs solar power? Because naturally, they use solar power to create their energies, but you use solar power to create your artificial electrons cycle, then you complete the remaining reaction. So would it have more potential if you allow the bacteria to do its natural course, but use the bacteria's natural energy to maybe conduct your further experiments? So yeah, I'm not sure what's the purpose.
Okay, very good question. A simple answer to that is that currently the well, first of all, what I propose there is not a traditional artificial photosynthesis. Okay, there are many people call what they do artificial photosynthesis. I never define exactly what it is. Okay, the purpose of what I do is to find a way to store electricity. Okay? As I said, one of the major problems of electricity is we don't know how to store it. Okay, we have batteries. As I've demonstrated, and you probably experienced the same thing before, battery is not stable and it's a lot of problems. And I used many charts to demonstrate that battery technology is allowed to improve. Okay? It's expensive and so on and so forth. So if we can convert this electrical energy to some other forms of energy that can be stored, then we make some progress. Okay, so thinking in terms of that, how many different forms of energy is there? There's electrical energy, there's thermal energy, there's a chemical energy. Now, people have used thermal energy, so use electricity to heat up things and then use the high temperature materials to generate as a storage. And then when we need it, we use that to regenerate power and energy. That's thermal. How about chemical? If we can convert electricity in the forms of chemical energy, and when we need to, we then convert chemical energy to whatever form of energy or materials we want. That is the purpose. And like I said, everything that scientists propose is only in the beginning, not in the final solution.
Thank you.
Along the same line, I challenge every one of you, take out your cell phone. And you know that, I'm sure you have a cell phone in your pocket somewhere, right? Now, how many little devices are there in your cell phone? There are so many integrated circuits, so many transistors inside. When are they invented? When they are first invented, did anybody would imagine that someday we will use a cell phone like that? And for older people, I'm sure 20 years ago, when people tell you that you can watch TV on your cell phone, you may ask, why? What's the purpose? Can you wait? Why do you need to watch TV on your cell phone? And even if you want to do that, it's not possible. It's too expensive, too little, too late. And yet today, we are talking on the phone with your parents. You probably talk to your parents on cell phone, see your mother's face every day. At least your mom wants to see your face every day. Right? And we see that every day, and that kind of transformative change happens so rapidly. And the interesting thing is that in the past 20 years, we have seen dramatic improvement in science and technology in other sectors, but we have not seen very much in this sector yet. So it requires a lot of bright young people like you guys to participate in this research, to make things happen, and not be discouraged by a lot of challenges.
President Liao, due to the time limitation, shall we open for the last question?
Okay. Yes.
Hi. My name is Ethan. I'm from Taiwan. So we all know that the greenhouse effect is a lot of gases from CO2 and CH4, right? So is that a way to decompose some like pig poo-poo to decompose that, because pig poo-poo has have the air pollution because of the CO2 and the CH4. So I want to ask, is there a way to decompose? Thank you.
Well, making CO2 and methane is exactly the way to decompose pig manure, okay? Or pig droppings. That's exactly the nature's way to decompose that. To take everything into the smallest piece and oxidize it, to take the oxidative product, the CO2, and the reducing product is methane, and that emits into the atmosphere. So this is how nature evolved. And chemical nature also demands that this is the final product. There are ways to avoid methane evolution, and people have tried that. That's possible, but it will make something else. Yes.
Thank you.
Okay. Thank you.
Okay. Thank you very much, President Liao. Thank you very much for such an inspiring lecture that you have given us this morning. I believe that you will be really influential to every one of us here. 我们再一次以热烈掌声来谢谢中央研究院廖继志院长，好吗？ A big applause again. Thank you very much. Really appreciate it. 今天非常感谢所有的来宾、老师、同学的参与。那么在今天结束之前，我还有几件事情提醒大家。So before we close this morning, I would like to give some reminders to you. 第一件事，请大家记得随身携带的物品 ，Please take your personal belongings with you. 第二，请参展的同学所有参展的学生到 B1 来参加学生交流午餐会。So all students, please proceed to B1 for a luncheon and ice-breaking event. So all the students, please follow. Make sure that you follow these two beautiful young ladies. Okay? All the students, 所有学生一起跟着这两位台湾女同学到 B1 去用餐。And teachers participating science educators workshop, please proceed to the east wing on 8th floor and please follow this gentleman. All teachers. 请所有参加教师工作坊的指导老师到8楼东侧休息区参加，也请跟着我们这位穿格子条纹衬衫的同学。最后一件事情 ，and the last one， 下午4点公布安全审查的结果，请各位同学要记得到1楼、8楼和9楼的公布栏来check， 还有台湾国际科展的网页也可以查看。The results of safety review will be posted on the bulletin board on 1st floor, 8th floor, and the 9th floor, as well as in the website, event website. So here now we mark the end of the opening ceremony of 2017 Taiwan International Science Fair. We again thank you for the participation and wish everyone great achievements in the event. 再一次谢谢所有贵宾今天的莅临，同时也预祝这一次所有的参赛同学能够获得佳绩，谢谢。